Good morning, class. It's what day is it? It's the 24th. It's Friday at about 7:41 a.m. And we're going to continue. I'm going to try to press forward today and finish this primary secondary, get these things posted, and then I'll be sending you a homework assignment or the last half of your project here probably this afternoon. But I want to get these lectures finished on primary, secondary. So here we go. We're down to 25, one pipe primary main design. So this is probably the most in-depth design discussion in this document, and I think it's pretty good. Just kind of points up some of the flexibility and variations on the primary secondary piping arrangement. So let me just jump down here. So one pipe says that we just run one and it comes all the way around and brings the water back. And so if this is our boiler, compression tank, air separator, suction on the pump, discharge on the pump. And so this is it. In this example, we'll go through this, but so we're pushing 110 GPM of 240 water. We pull some water off to the first circuit and we dump it back in, and guess what? The temperature goes down because in this case, we're going to take 200,000 BTUs an hour out of this primary. And so this is cooler water coming back. We dump it into the 240, which we have here. They mix, and so we reduce the temperature. We go down to circuit 2 and we pull some more water out at this reduced temperature going in. We take heat out of that, we put it in, it gets cooler yet. We come around to circuit number 3 and we take some more heat out, it gets cooler, and then it's going to be the coldest over here. So your primary supply temperature is not the same around the loop, but you're saving pipe, right? Because you only running one pipe all the way around here and back to the boiler. So, it's interesting. Okay, so let's see what the notes say here. The one pipe primary distribution main has unique advantages over the more conventional two pipe because balance is automatically established by the design procedure and because of cost saving possibilities. So we take care of balance as we design this thing, I guess. The one pipe design is predicated for either heating or cooling on each secondary circuit having primary circuit water temperatures available to the secondary circuit, which will meet secondary circuit requirements. Because if on a heating situation, that water is going to get cooler the further around the loop you go, and you got to make sure it's still hot enough to provide whatever heating you need at, say, your last couple zones. On the cooling side, that water is going to get warmer because you're going to, put some heat in and then dump it back in and mix it after the first circuit, and so it's going to go up all the way around. And so I'm really skeptical about this on the cooling side. I just don't think you're going to see it, and I doubt you're going to see it very much on the heating side. But from an academic perspective, it's pretty interesting to see how all this can be done. Okay, so our example here is the same 4 circuits, the same loads that we had before that we've already worked with. Circuits 1, 2, 3, 4. You see circuit 1 is 200,000 BTUs an hour. Number 2 is 2 million BTUs an hour. 3 and 4 are both 500,000 BTUs per hour. And this is a heating example. We see the description of the type of equipment: baseboard, fan coil, panel, and air handler. And we have the, I guess we're using the same, these are the secondary circuit flow rates. This is not primary. And so we have the same temperatures. We selected the same supply and return temperatures. And so we'll be using this, especially this column over here, 190, 130, 100, and 170 for the return temperatures for the circuits 1, 2, 3, 4, respectively. Okay, so let's get into this a little bit. So we see that this last circuit over here requires 190. So what that's saying is this water, we're going to pick a supply temperature, and obviously they're going to pick 240. When you get past these first three circuits and get over here, we have to have 190 because that's the supply temperature required for circuit number 4. So that's what he's talking about here. The last circuit, number 4, requires 190 degree Fahrenheit supply temperature for secondary circuit design conditions. So given or selected 240 primary supply temperature, the primary circuit can be designed for a 50 degree delta T for the load represented by the first 3 circuits. In other words, if we're going to start at 240, we can't go below 190 over there as we approach the last circuit because it's got to have 190 supply temperature. So we use that to size the flow rate. So you take the loads on 1, 2, and 3, you add them up, and that's the 200, 2000, and 500. So what is that? That's 2,700 MBH, or 2.7 million BTUs an hour. And at a 50 degree delta T, that comes out about 110 GPM. So that's Q is equal to 500 GPM delta T. Q is 2,700,000 is equal to 500 times GPM times a 50 degree delta T. If you solve that, you're going to get roughly 110 GPM. They do round things off a little bit in this. So the 110 GPM flow rate will provide 190 degree supply water going up to circuit number 4, and represents a total 1 pipe circuit temperature drop, including circuit 4, of about 60 degrees. And so you can calculate that. So we remember we've got 3.2 million BTUs per hour total load for all 4 of these circuits. We're going to circulate 110 GPM. So, what, 3.2 million divided by 500 divided by 110 will give you approximately 60 degrees on the delta T. Okay, so that's not too bad. So then now we can start laying out this 1 pipe primary system. And so this is kind of what it looks like. We've got our boiler and our air separator compression tank. We got our pump. So we're coming out of the boiler all through here at 240. So we're showing pump discharge 240. We get down to circuit number 1, and we're going to take some undetermined amount of water at this point, this hot water up here. We're going to return it cooler. It's going to mix, and we're going to have a reduced temperature here. We're going to take this reduced temperature, then is what's available to circuit number 2. We'll take some of that water up here. It'll come back cooler. It'll mix again here, and then so we'll reduce the temperature further. We do the same thing at 3, and we know it's going to be 190 over here at the exit of 3 going over to 4, because that was our selection criteria when we selected the 240, and then we calculated the 110 GPM based on that. Okay, so what's this temperature? How do we determine this? Well, we've got 110 GPM. We've got 240 degrees over here, and we're going to take out 200,000 BTUs an hour. So, I mean, that's pretty simple. Get your calculator out and put 200,000 BTUs an hour, divide it by 500 for the constants, and divide it by 110 GPM, and that comes out 3.6. Okay, So what that tells you is that's going to reduce the temperature 3.6 degrees of that total flow rate after it all comes back together and mixes over here where we've got this temperature question mark sign. So if I take 240 minus 3.6, I get 236.4, and they're just going to round it to 236. And so you can continue that process at this location. And we'll do some of that down here. So let me shift on down. Okay, so he's done that. And so here are the temperatures from 240, we go to 236. Here we're going to drop to 200. Here we drop to 190. And here we drop to about 180 for when we've satisfied all of the design loads for the zones, and we're headed back to the boiler to reheat. So we've got, what is that, about a 60-degree delta T on this system. Okay, so let's go ahead and just run this second number for you. So this circuit is going to take out 2 million BTUs an hour. So if we say 2 million, and our primary flow rate is 110, so I want to divide by 500, divided by 110, and that comes up 36.4, but he's going to throw that away. So we're going to drop the overall temperature of this 110 degrees, the 110 GPM, 36 degrees after we take out 2 million BTUs for circuit number 2. So we were 236 here, so we're going to reduce it 36, so that puts it to 200. And so we just continue all the way around the loop. Okay. Okay, let's look at secondary control methods. The secondary control methods used for one pipe primary main secondary control depends on several factors. What we select depends on the ratio of injection riser to secondary circuit flow or to primary flow, as we'll see. That was to determine if the two-way valve would work. We had that discussion, I think, the last video of the last lecture. Location of common piping, location of pressure drop for riser flow, and start-stop. Okay, those three. And now we're going to first look at start-stop pump control. Okay. So what happens here when you have this one pipe primary system where we connect the bleed risers in order to get flow, say when this pump starts, you have to put in this restrictive pressure drop, either here or we'll find out later it could be down here, in order to cause flow to occur from this primary into the secondary. Now, if we go back up, I think it's figure 16. I did some looking before. Let me see, figure 15. Yeah, this is fine. Okay, so with a two-pipe primary, we don't have to put a restrictive pressure drop in because there's a delta P between the primary supply main and the primary return main. So, you know, even before you build the secondary, you can build the crossover, and this delta P then will establish the flow rate, and we simply put a balancing valve over here and a balancing valve over here to get whatever primary supply GPM that we want. Because I've got a delta P between here and here, in order to make that flow occur. When I come down, where was I? Forget exactly. Yeah, I jumped too far here. Yeah, this is where I am. Okay. So this is just the same pipe. And so these connections are close together. So without something up here, the restrictive pressure drop being put into this thing, when this pump runs, you probably get some flow, but there's no way to really balance and determine how much flow is going to get pulled up here versus here. It depends on how long this line is versus how long this line is up here, because from here around to here is common. I mean, it doesn't change. So the only variation between when you want flow up here and when of course, I mean, when this pump comes on, to control it, you have to put in this restrictive pressure drop. I guess I'm talking around in circles, but anyway. Okay, so when start-stop operation of the secondary pump is used for control in the one pipe application, the injection riser flow rate is induced by a restrictive pressure drop on the order of 1 foot pressure drop, whatever, it's balanced in order to, what they do, they run the pump, they measure this flow, and then they adjust this pressure drop in order to give us the desired flow when the pump runs. Okay. Okay, another way to do it is with injection pump control. In this case, then we're going to pump the secondary continuously, so continuously operating secondary pump. And then we have the injection pump that when we need heat up here, the thermostat or sensor kicks on this pump, and then it pulls water out of here, puts it back into the main, which causes water to flow on this side back up through the injection riser. And of course, we've got a balance valve over here that gives us the proper flow based on the pump selected. Okay, so that's a little bit different. And I guess, let's see, did we have temperatures? I guess we did have temperatures on both of these. I kind of glossed over that. So in this case, we'll see that we're sizing this for 8 GPM, and we'll have 12 across the restrictive pressure drop. They'll mix here, and this gives us, I think we wanted, it's a 20-degree delta T, so I'm 190 on the return, so I got to be 210. Yeah, I'm 210 over here at 20 GPM going through this. And so then that puts me with 8 GPM at 190 that's coming back and mixing at this T, which is going to then cool down my total flow of 110 GPM from 240 down to 236. Okay. And so I've got the same temperatures basically and flow rates here. Okay. I don't think there's anything else there that needs to be discussed. Injection pump application is simple and does not require specific application rules. So pretty easy to make this work. Okay, the two-way modulating valve control. So there's a couple ways to pipe this up. This is kind of interesting. So this is kind of traditional. This is basically what we kind of saw before with this two-way valve. If this valve is wide open, we're going to have to put some sort of a pressure drop someplace. In this case, we're showing it up here in the secondary. And again, this valve open, you put your restrictive valve here, you put your flow meter on here, and you adjust this valve so that I get my 8 GPM through the bleed riser with the valve wide open. And then of course, as the valve modulates shut, as it starts closing, you're going to get less and less flow up here. When this shuts completely, you'll get no flow up here. Okay, so that's same flow rates as we had on the previous diagram. Okay, another possibility, this is kind of, this was not intuitive to me, really, until I read this a couple of times. But you could put the restrictive pressure drop down here in the main, in which case that would switch the common pipe actually up here to the secondary. And this will work because when this valve is open, we can block pressure, we can back pressure up a little bit here, which then will force the appropriate amount of flow up into the secondary when we need heat. So this will work as well. Now, what's interesting is if we go back up here when we were doing this two-way valve stuff, okay, no, not yet. That's it. There we go. When we had this discussion, let me make that a little bit. There we go. This was, now this was in the secondary, the way we do it before. But in order to determine whether this two-way valve control was going to give good controllability or would, from open to shut, would reduce or alter the flow in the secondary, the total flow in the secondary just based on the valve position, which was not really acceptable to get a lot of variation there. We calculated these ratios. So, and we had this table, and remember we wanted to be up in this portion of the table. So this is percent riser input flow to secondary flow. Okay, so in this diagram, it's what's up here divided by what this pump is circulating. Okay, and this had to do with the drop across the restrictive compared to the total pump head. Okay, so you may need to go back and review that. There we go. Now let's make this a little bigger. Okay, so two-way modulating valve control finds particular use in one pipe primary main application. So they really recommend it, especially here. This is because the governing flow ratios, and that's back up to that table we just looked at, can almost always be set less than 30% by use of either figure 92 or figure 93. And the difference, figure 92, I get them both up there. See, here the restrictive pressure drop is in the secondary, and here it's in the primary. Well, so let's see how these flow ratios change based on the location of this basically a balance valve that causes the restrictive pressure drop. So in 92, we take the injection riser flow, which is 8, and divide by the secondary circuit, which is 20, and that ratio comes out 40%, which is too high. So say this, for this particular circuit, this is not a good location for this restrictive pressure drop. So in this case, we take the 8 GPM here divided by the 20 that's up here in the secondary, and we get 40%, and we go, that's no good. But if we check out this one, because the restrictive pressure drop is down here, we're going to take the 8 and divide by 110, and all of a sudden that becomes 7.2, and that's excellent. So this is the configuration that we would want to use as far as the control, the space temperature control on this first circuit. Very interesting. Flow ratios are less than 30% for figure 93, and application can be made with assurance of exceptional controllability. So that's good. We like to be exceptional. When two-way valve control is applied to one-pipe primary systems, the restrictor pressure drop should be applied in a location, either one of these two, which will yield the lowest percentage flow ratio, below 30%. This is illustrated below for the design example. Okay. So I guess this is not really part of our example. This is just an example. Okay. So this is where we apply it to the circuits that we're looking at. And you need to spend some time and really study this a little bit. After you study it a while, it does start making pretty good sense. Okay, so circuit number one. Just a second, I'm going to close the door here. Sorry about that. My wife's on the phone in the other room, and I'm afraid it's going to bleed over. Okay, so circuit number one, here is our 8. And so if we were to put the restrictor up here, then the ratio would be 8 divided by 20, 40%. So this is one we've done, I guess. And then if we put it down here where it's shown, that makes the ratio 8 divided by 110, which is 7, 110 through here. That's 7%, and that's very good. So this is the way it got drawn up because that's the way you want to install it to get better controllability. Okay, moving on to circuit number 2, and we want to use this two-way valve if we can get the flow ratio to be low enough. Okay, and so now we're going to show it up here in the secondary because I've got 200 GPM flowing in my secondary. This is a great big circuit, okay? And I've got 39 going through my bleed riser. So if I put the valve in this location, my ratio is 39 divided by 200, which is 19.5, which is pretty darn good. If I put it down here like I did over here, then it would be 39 divided by 110, which is 35%, which is not so good. Okay, so I show it up here in the secondary. Likewise, come along to circuit number 3, and I need 11 GPM for my riser flow, and my secondary is 50. So if I put it here, then that ratio is going to be 22%. If I put it here, that ratio is 10%. And so that's much, much better. So I show it here. And over here, when I check my ratios, I just can't make it work. So I'm going to have to do something else. It says, do not use two-way valve with circuit number 4. We'll do something else here. Okay, so y'all need to study that, make sure you understand it. The restrictor pressure drop for two-way modulating valve application would generally be set for approximately 3 psi delta P, and the control valve that should say sized accordingly. Using circuit number 1 as an illustration, we would get this. So this would be set to 3 psi, and for this to be 3 psi, you can use your Q is CV times the square root of delta P over specific gravity, and you would find out that you need a CV of about 4.6 in the wide open condition. And so this pressure drop and this pressure drop are size approximately the same to make this work. Okay. Let's see. Three-way valve application to one pipe primary main. The control valve application that should be made to circuit 4 would be a three-way bypass or diverting valve. And they like the valve on the back side of the coil for air considerations, as we've talked many times before. And the secondary circuit as described in 92. So this is the way we would control that fourth zone. So we've got 110 coming up at 190. This is CV sized, and when this valve is wide open, we should get 50 GPM up here. We mix to get, let's see. Now this is all fit. That's right. There's no mixing on this one because this is our 190. We need all the 190. So we get full flow up through here. We get our 190. We get 170 here, comes back, goes back into the primary main. Three-way valves will not often need to be applied to one pipe primary main secondary circuit control because flow ratios generally prevent two-way valve application, and that's what we prefer. The bypass or diverting valve application is preferred over the mixing valve when applied to secondary circuit because pressure drop problems. That's what they want. They want this pressure drop on the backside of the coil. Just a comment, one pipe primary main chill water, several large central station distribution systems have been installed using one pipe chill water distribution mains. Complete design satisfaction has been obtained. Design is sophisticated, requiring integrated attention to temperature rise down the main and diversity factors. I don't recommend this. I don't think you're going to see it very much, and I don't think you should really consider it most of the time. Okay. I'm going to go ahead and cut this off here, and I'll come back with one more time, and we will finish this. Hope you guys have a great day, and I'll be back in touch shortly.